Swayam Prabha. Digital India. Educated India.
Hello all. So we have been seeing a series of advanced passive strategies, and as one amongst them, today we will see another advanced passive strategy, and that is the wind tower. It's a very interesting strategy because there is nothing new about this strategy. These are called as wind towers or even wind catchers. So they are called by different names. Now, wind catcher is a traditional element that has been used as a passive cooling technique in hot, dry regions for many centuries. They are known by several names such as wind catcher, wind scoop. They are called as Malkaf or Badgir, which is actually a wind tower, and it's a cooling architectural feature. They are called as butting in Syria. Even Egyptians call it the Malkaf. It's called as Badger or Baudgir in Iran, Iraq, and Pakistan. It's called as Kastil in Bahrain. It's called as Badkir in Qatar. So, wind catchers have been used for centuries and they have had different names. So, wind catchers are attributed to the Persians by some historians and archaeologists, while others think the first examples were constructed in the North African deserts, especially in Egypt. Now, wind catchers are a natural solution for climatic problems in hot and dry climates, and they are used in North Africa, West Asia, as well as in India. So, it's an architectural feature and a spatial devices constructed on the roof to extract fresh air into the rooms and the interior corridors of the building. It provides passive cooling and is also a source of natural ventilation to the building. Tall towers, wind catcher, rooftop vents, these catch the wind, cooling the interior spaces. If we look at the function of the wind catcher, there are two functions. The first function is to catch the prevailing wind and direct the wind into the interior spaces of the buildings. The next function is to extract and remove the stale air or the polluted air outside. Thus, it helps in supplying fresh air and generate clean ventilation. The working principle of the wind tower is that it works on the principles of natural pressure and temperature differentials. Air movement is created by the rising of warm and the lowering of cool air. As we have already seen, warm air is light, it rises up, and cool air is heavy and it tends to settle down. As the air above the land gets warmer, it rises and creates an area of low pressure because, in a way, it forms a vacuum. It's not exactly a vacuum, but then when the air rises, then there is a low pressure formed. When air continues to rise, it moves towards water surfaces where it falls and creates an area of high pressure and pushes cold air towards the land. This movement is what creates the wind, and this is the basic or very underlying concept of a wind tower. The Badgir or wind catcher functions by trapping the faster moving air above the dense settlements of the region. It exploits pressure differentials existing between the vents above roof level and room outlet level. These towers, they work by directing the cool air that is circulating at higher levels with high density. This is pulled down and this air enters the interior space with higher pressure. Once the cool air enters the space, the warm air circulating inside the interior space is pushed out through openings created on the opposite side. So, if we look at the rise and evolution of wind tower design, the Pharaonic era, which is the era of the pharaohs. Pharaohs were the Egyptian kings. So they had a variant of wind catcher which would look like these. So these were in a sense wind catchers. Then during the medieval and Ottoman eras, knowingly or unknowingly, during the medieval and Ottoman eras, there was a very conscious decision to create structures which will bring air and create structures as outlets because warm air would rise up. Then this has also been demonstrated in the Mosque of Al Salil Talai. This is in 1160 AD and you can see a small vent here which initiates and generates wind movement inside. The Christian hermitages in the desert of Esna shows that there is airflow in the hermitage in the desert of Esna through these, no, they were not towers, but definitely there were channels used to direct and trap the breeze with outlets. The Khanka of Sultan Babybars also had consciously designed towers to suck in the outside air. So these were all variants, initial variants of the wind catcher. The Khalifa Stadium in Doha, Qatar has very consciously designed a wind tower. Now, the conventional and traditional wind towers were of different types. The first is a one-sided wind tower. The second is a two-sided wind tower. So, a one-sided wind tower had inlets only on one side, whereas a two-sided wind tower had openings on both the sides, on this side as well as on this side. The 4, 6, 8-sided wind towers had multiple openings on all the directions and it used to be tower over tower. And then there is the cylindrical wind tower which is actually in the form of cylinders and has inlets on all its sides. Now, wind towers also have certain limitations. The Badgir has an opening with no protection, which means if it rains, then there is a potential for precipitation or water to enter inside. But wind towers are most effective in hot and dry condition and precipitation there is pretty much low. But it still provides a vent for insects to enter inside. The cooling potential of wind catchers are limited. So there is only that much a wind catcher can work because the outside air itself is warm. Then four-sided badgear on the roof, it has the fresh cool air drawn from the building by one of the sides. It gets mixed by the warm air being drawn out by the other three sides. During the winter, the traditional badgear still allow cold air into the building and shifts the warm air out. They do not have any applications in regions which have very low wind speed. So the wind speed has to be high. If the wind speed is low, then the badgear or the wind tower does not have any function or any effectiveness. Let us look at the working principle of the badgear. So, a badgear's ability to function is influenced by the temperature and wind speed of the day. A badgear can operate in four primary modes, switching between intake and outflow functions. When there is no breeze at night and the badgear's temperature is greater than the ambient temperature, then through the apertures in the tower, the badgear draws air upwards and forth just like a chimney. The walls of the badgear, especially the interior walls dividing the air passages, they collect heat throughout the day and then release it into the colder air within the surrounding the badgear tower. Warmer air has less density, which lowers the air pressure at the top of the tower and produces an upward draft. Cool ambient air is brought into the building through the doors and windows from the courtyard as a result of the tower drawing up the air inside the structure. The night air, when that air descends, the badgear cools the chambers as the air is forced down it. Here, the cooling can still be successful enough to bring the building's temperature close to that of the outside air, even when the tower walls warm the night air before it reaches the structure. When there is no breeze during the day, what happens? When there is no breeze during the day and the badgear's temperature is lower than the ambient air temperature, the badgear functions similarly to how a chimney does. The outside air is hot and the hot outside air hits the badgear's walls, which have been chilled due to the air from the previous night, because night sky is a big sink of cool air. It flows down the badgear and gets thicker and colder. When I say thicker, I mean it becomes denser and cooler. The badgear walls warm up as a result of absorbing heat from the surrounding air. The airflow down through the tower and into the building stops when the temperature of the badgear reaches or surpasses that of the surrounding air, and the tower starts to function more like a chimney. The fourth condition is when there is wind during the day. When wind blows into the badgear's vents, it is driven through it and cools down because it comes into contact with the walls. Now, let us look at the elements of the wind catcher. The roof, the shelf, the stalk, the blade and chimney are the components that make up a wind catcher. What is the roof? Now, roofs can offer in several forms. Three types of roof wind catchers are available. One is a flat, another is slanted, and third is curved. Second is shelf. The shelf that houses the blades and the air passing channel in the wind catcher head is called as the shelf. Stalk. So, the stalk of the wind catcher is the portion that sits between the shelf and the chamber. The taller the wind catcher, the taller is the stalk. Then the fourth element is the blades. So, blades are the components where brick and mud brick, which split the shelf into smaller ducts, happen. Let us look at the factors affecting the efficiency of a wind catcher. Now, first is the height. Height becomes very important. So, wind speed and wind catcher height are directly correlated. More the height, better is the working of the wind catcher. Second is the wind catcher's cross section. The shaft size and the volume of air admitted into the building are directly correlated. So, bigger the shaft size, more is the volume that it can accommodate. More volume of air can be accommodated for movement. Third is the intake and exhaust openings, because these impact on velocity. The outlet entrance is close to the ground while the entry aperture faces the direction of the wind. So you need minimal quantity of aperture for outlets. So the wind direction and the long axis of the wind catcher entry, they must be aligning with each other. Air speed decreases with more number of openings, and air speed increases when minimum number of openings are provided at the outlet. So, here the speed is decreased, whereas here the air is capable of gushing out when the opening size is small. Let us quickly look at the case study of the Torrent Research Center in Ahmedabad, which has used a number of wind catchers in their design. So, the Torrent Research Center is in Gujarat, India, and it is a complex of research laboratories with supporting facilities and infrastructure. It is located on the outskirts of Ahmedabad. This building uses passive downdraft evaporative cooling for large-scale office buildings and demonstrates that it is possible to achieve human comfort in dry, hot regions. So, in plan, you can see the wind catchers here in section, and also this entire system in the center. They operate together. So, you can see this functions as the inlet, the center one. Here in the wind catcher, they have placed water for increasing the humidity, and it functions like a passive downdraft evaporative cooler. But during certain months, the sprinklers are not operated to enable airflow into the building of appropriate temperature through the baffles and the outlet air is taken out through the exterior chimney or the exterior wind catcher. So as we had already seen, during the cool season, the strategy that they use is different from that of the warm season and from that of the monsoon season. So based on the season, the outlets are closed or the inlets are closed or the sprinklers do not function. When sprinklers do not function, it operates more like a wind catcher. Let us look at the second case study, and that is the classroom building located in Erbil city in Iraq. In this study, an IESV sustainable tool as well as CFD is used to examine the efficiency of the passive system on 3-floor classrooms in a hot arid climate, which is Erbil city. Now, if we look at the physical attributes of the base case model, glazing is assumed to be clear and single glazing and covers a 14% window to wall ratio. The construction of the walls of a single uninsulated leaf wall with a concrete block is used. The classes have a dimension of 8 meters by 5 meters by 4 meters. And you can see that here you can see in the proposed case, the study is done to understand what happens when the tower height is 3 meters, what happens when it is 6 meters, and what happens when it is 9 meters. For the base case for which the plan is shown here. So, IASV model of the 3 alternatives with the height as 3 meters, 6 meters and 9 meters is considered. So, wind catcher is more effective during the early morning than in the late afternoon, with 3 degrees difference in temperature between these two periods. The findings showed that increasing the height leads to enhanced wind catcher's performance in terms of bringing down the mean radiant temperature and also by increasing the number of hours within the thermal comfort zone. The tower, which had 6-meter height, gave the best results because it raised the percentage of hours within the comfort to more than 75% of the total hours. In the study, it was found that the wind catcher is more effective during early morning than in the late afternoon, with 3-degree difference in the temperature between morning and late afternoon. Increasing the wind catcher height is better to enhance its performance because by doing so it reduces the mean radiant temperature and also increases the thermal comfort hours. 6-meter height seemed to give the best results. Wind catcher also has an impact in bringing down the energy demand of the cooling system. Raising the height of the wind catcher will lead to a better performance, but it is not supposedly shown in this study. When the outdoor temperature is maximized to say 31.5 degrees centigrade at about 1:30 p.m., the wind catcher room temperature is shown to be 27.5 degrees centigrade in model 1, and it shows about 28 degrees centigrade in model 2 and shows 28.5 degrees centigrade in model 3. Hence, these kind of wind catchers can decrease the temperature between 3 to 5 degrees centigrade when the outdoor temperature is at the peak. So, outdoor temperature decreases gradually in the afternoon, but indoor air temperature also declines anywhere between 3 degrees to 5 degrees centigrade up to 4 pm time. The best performance seemed to be by the model 2, as the number of hours that the MRT mean radiant temperature was within the comfort zone for nearly 65% as compared to 60% for model 1 and 50% for model 3. So, you can see the mean radiant temperature of the second one, model 2, performed better up to 1 o'clock. But after 1 o'clock, it was model 1 which performed better or similar to model 2 until midnight. So, between midnight to 1 pm, model 2 worked better, whereas between 1 pm to midnight, it was model 1 which was equal to or better performing than model 2. And there was a difference of approximately 3 degrees centigrade to 5 degrees centigrade difference between the outside mean radiant temperature and the indoor mean radiant temperature. Let us now look at the application of wind catchers in the contemporary context. So, wind catchers, they utilize wind and renewable energy to improve the quality of indoor air and also increase the thermal performance in buildings. So, these uses can be found in Pakistan as well as in India. Using certain roof elements to increase the ventilation of buildings is a concept which we have derived from vernacular architecture of the Middle East, and contemporary architects have also tried to adapt this in their modern buildings. This they do in order to take benefits of the traditional wind catchers and eliminate their limits to adopt them with improved building types and technologies. Many modern and commercial wind catchers have been used. Today we will see the example of the University of Qatar in Doha. This was built in the year 1985 to 1991, where in the design itself they have integrated with a new type of a very simple wind catcher with many openings on each side. Another different example is the French school named Lycée Charles de Gaulle in Damascus, Syria, with a design to revive the use of local materials and also bring in passive design strategies for natural ventilation. When it comes to the University of Doha, at the University of Doha, each chimney works independently as a thermal regulator to regulate the interior space. The vents are oriented towards predominant cool air, and they are staggered to avoid the blocking of these currents. The inside of each of these towers is divided into two parts to let in the warm air and also the cold currents to flow without mixing each other. First, the lower temperature air or the cold air passes through the opening of the vent. It hits the interior wall. Because of the stack effect, cool air with more density, it descends down because it is heavier. It comes down to the lower levels of the building, cools the interior space. Once this air cools the interior space, it means it becomes warm at the inhabitant level. So it ascends again to double height space and leaves through small openings which are located on the other side of the chimney. So this simple, passive and inexpensive process to bring down the air temperature at human body level makes the person stay cool throughout the day. There have been several interpretations of the wind tower in the contemporary context because wind towers, though they are an advanced passive technology, because we use another specific uh, attachment to the building, we call it as an advanced passive technique. But we have, but traditionally, wind catchers have been used in vernacular architecture all over the world, especially in hot and dry climates. It is an inexpensive method and an effective method which is proven over centuries. So, we stop our class with having discussed the wind catcher, and we will continue to discuss another advanced passive technique in the next class. Thank you.